So let me introduce Jonathan Mosheiff from the Computer Science Department at Carnegie Mellon University, who will talk about stability and testability from a computational perspective. Jonathan, please.
Okay. Hi. So thank you, Alex, and thanks for the invitation. So I'll start by saying that this talk is intended to be approachable both to group theorists, but also to people who are not group theory experts. And that's a population I empathize with because I myself am not a group theorist. So I apologize in advance if I'm going to be saying some things that are very obvious to many of you. But also, on the other hand, if I'm assuming anything that's not clear about either group theory or about computer science, then feel free. I encourage you strongly to ask so that we can have everyone understand. Okay, so our goal here is to show some recent work on connecting the theory of stability in permutations, which Alex gave an overview of last talk, to certain natural algorithmic and computational problems. So as is common when we're talking about stability, I'm going to start with the sample problem of the equation xy equals yx. So consider the following algorithmic question. Suppose we're given two permutations over 1 to n, and we want to determine whether these two permutations commute. So we want to check whether AB is equal to BA. And of course, this can be done in linear time. But the problem is, what if we don't have linear time? What if n is so large that even just reading the entire input would take too much for us? So it's not hard to convince ourselves that if you can't even afford to read the input, then you're not going to be able to fully solve this problem. Yeah, you're not going to get a deterministic algorithm that, given two permutations, always decide successfully whether they commute or not in less than linear time. However, we can relax this problem a bit to get something that is solvable and is actually very interesting. So in order to relax the problem, we're going to make the following definition. So first, we're going to denote by sol just the set of all pairs of permutations that commute. So these are the pairs for which we want our algorithm to accept. And then, given any epsilon, we're also going to define the set sol larger than epsilon. And these are the pairs of permutations, A and B, such that they are epsilon far from any pair which commutes. And by epsilon far here, we mean that let A prime and B prime be some commuting pair. And we measure the Hamming distances of A from A prime and of B from B prime. So the Hamming distance between two permutations is just the number of elements on which they don't agree. It's the number of x's such that ax is different than a prime x, and this is normalized. It's divided by n. Okay, so if the sum of these two Hamming distances is at least epsilon, we say that the pair AB is epsilon far from being a solution. Okay, and now we get what's called in computer science a property testing problem. So property testing is a field that's generally concerned with problems of the following sort. We want to test whether some objects either belong to some solution sets or is epsilon far from the solution set. I mean, we're doing a relaxation where we're okay. We don't really care what our algorithm does if the object is not a solution, but it's very, very close to a solution, like less of an epsilon, distance less than epsilon from a solution. In that case, our algorithm can do whatever. But we just want our algorithm to correctly be able to distinguish between solutions and those that are epsilon far from solutions. And generally, property testing is usually concerned with two types of objects, like classically. Either functions, like say, one of the, I guess, like the most classic problem in property testing is testing whether a given Boolean function is linear. And the other objects that are classically tested in property testing are graphs. And here we're trying to test a different sort of object. We're trying to test a pair of permutations. Okay. So this is the relaxation we're going for, decide whether this pair is epsilon far from a solution or is a solution, and we don't care what if, and we don't care about the middle case. And now we want to be able to do this in a very limited amount of, well, very, very limited number of operations. So let's define what exactly are we looking for, what sort of algorithm we want. So for a given epsilon, an epsilon tester is an algorithm that can query entries of these permutations. By this, I mean that I take some x between 1 and n, and I can in a single operation I can ask what is a of x for this given x, and now we want a randomized algorithm that satisfies the following properties. We want it to be complete in the sense that if the permutations commute, we want it to accept with very large probability, say more than 0.99. If the two permutations are at least epsilon far from commuting, then we want the algorithm to reject with high probability. And importantly, we want a constant number of queries. So constant means since we fixed epsilon, then this number of queries is allowed to depend on epsilon. And it's not hard to convince ourselves that this is necessary. We can't have the number of queries not depend on epsilon. But it may not depend on n or on the permutations themselves in any way. Okay? So this is the sort of algorithm that we're looking for. And now the question is there such an algorithm for every epsilon? Okay, so we'll be saying that this equation xy equals yx is testable for permutations if there exists an epsilon tester for every epsilon. Okay, and now a certain algorithm is if I just gave you this question, I guess the first algorithm that would come to your head, or probably maybe just did for some of you, would just be the following. So what can we do with a constant number of queries? So note that given a certain x between 1 and n, using 4 queries, I can test whether the permutations commute on this specific x. Okay, so I make one query to determine a of x, then another query on that to determine what is b of a of x. Then I do the opposite to determine what's a of b of x, and then I just check whether they're equal or not. Okay, so this yields what we call the sample and substitute algorithm with repetition factor k. What it does for k independent iterations, it samples some x and does exactly that. Now, if it found some violation of the constraint that the permutations commute, then it can just, it knows, right? In that case, we know for sure that the permutations do not commute, so we can reject. If it didn't find any violation within these k queries, then we can say, OK, we haven't found any violation. One might exist, but let's just accept. So this is sample and substitute. It's a very natural algorithm. And now the question is, does this algorithm for some k satisfy the definition of an epsilon tester for AB equals BA? So in order to analyze this algorithm, I'd like to make another definition, which is called the local defect of a pair of permutations. So the local defect is just the number of x's on which the two permutations don't commute. Okay, so formally it's the Hamming distance between the permutation, the normalized Hamming distance between the permutation AB and the permutation BA, and this is exactly the number of x's in which AB does not equal BA. And this is exactly equal to the probability that in one given iteration of sample substitute, the algorithm would find the violation and reject. Okay. Is everything good so far? Okay, please feel free to ask questions if you have any. I might not see the chat, so you can just also just barge in if you want. Okay. Okay, so given this definition of local defect, we can now analyze the sample steps in the substitute algorithm. So this algorithm is trivially complete. In fact, right, so what does it mean that it's complete? It means that if AB and BA commute, then obviously the algorithm is never going to find a violation, and in that case, it always accepts by definition. So not only is it complete, it's actually more complete than we required in our definition for an epsilon tester, because we allowed the tester to be mistaken in the case that AB equals BA with some small probability, but here it's actually never mistaken in that case. So that's good. What about soundness? So as we just said, right, so the probability that we're going to reject the permutations in a given iteration is just equal to the local defect. So the probability that all k permutations will accept, all k permutations would not find any violation, even though there is a violation, is just 1 minus the local defect to the k. So we want the acceptance probability here to be, in this case, to be small. We want it to be less than 1 over 100 by definition of an epsilon tester. And like this is the probability that the tester is wrong. So to get epsilon soundness, we need that for every pair A and B that is at least epsilon far from being a solution, right? So 1 minus the local defect to the k should be less than 1 over 100. And this just by taking a log and rearranging, this basically means that k needs to be some constant over the infimum over all A and B's that the algorithm may encounter, right? I mean, I'm taking the infimum here because we need to be ready for the worst case. The worst case here would be a pair AB with the least local defect among all these pairs that are epsilon far from being a solution. So we basically want k to be some constant over this infimum. So we want to take k that satisfies the soundness condition, but is as small as possible because we still want to be as efficient as possible. So we're just going to take k equal to this log 100 over this infimum. And now what do we get for efficiency? So the algorithm, the number of queries that the algorithm makes, as we said before, is 4k, right? Because each iteration we just need to check a of x, b of a of x, and the opposite. So it's 4 queries per iteration. And we need this k, okay? We need this 4k, which is just like k itself. We need this to be fixed for a given epsilon. So this is going to be fixed if this infimum is not 0. That is, if there exists some delta that may depend on epsilon, but definitely not on n, such that the local defect of every pair of permutations that are epsilon far from a solution is at least delta. So to summarize, if this last display equation here about the L defect being larger than delta is true for every, like if we have this condition for every epsilon, that would be equivalent to saying that the sample and substitute algorithm is a tester for x, y equals yx. Unfortunately, this is true. So we know this is true by a theorem of Argentseva and Paunesco from 15. It's actually a stronger theorem about stability of abelian groups, but the part that we need here is exactly the statement we wanted before. Like for every epsilon, there exists some delta such that the local defect of every two permutations that are epsilon far from solving xy equals yx is larger than delta. And of course, they stated it a bit differently. They stated it as, say, the group z square is stable. And we're going to get to that soon. But this is essentially what the theorem says. So equivalently, we can say that this theorem says that the equation xy equals yx is testable by sample and substitute algorithms. And moreover, I can also mention another theorem of Oren Becker and myself, which says that not only is the local defect bounded from below by some delta, but this delta is actually not that small. It's some polynomial in 1 over epsilon. So this means that not only can we test this equation using sample and substitute algorithms, but we can do it by taking k whose dependence in epsilon is polynomial in 1 over epsilon, and not say, like it could be it could be in theory a much larger function of epsilon. So in that case, it's not. Okay, so that pretty much settles the question of the testing xy equals yx in permutations. And of course, we're going to be interested in general in testing a general system of equations. So the framework for a general system of equations, I'm going to go over this relatively fast, although I'm not going to assume that everyone here knows exactly this framework. Okay, so we're going to fix a system of equations which are of the form wi1 equals wi2, where these wij's are just words in the free group over some fixed alphabet s. So just for those of us who are really not from this field, the free group is just the group consisting of all words over this alphabet and their formal inverses with concatenation. So it's basically just words that we can write using this alphabet. Given given a tuple of permutations, we want to say what it means that this tuple of permutations satisfies the equation. So in order to do this, we need to be able to somehow substitute a tuple of permutations into a word wi1, into the words wi1 and wi2. Okay, so we just do that exactly as expected by substituting each permutation sigma I in a tuple of d permutations. We're going to substitute the permutation sigma I for the letter si from the alphabet. So you can just see an example here how we take a given word and we substitute a permutation naturally for the letters in this word, and we get some resulting permutation.
Jonathan, is there any reason that you want 2 words rather than 1 word and like 1?
No, it's so yeah. So obviously you could always just move right. I mean, you can always just, instead of writing wi1 equals wi2, you could also write wi1 times wi2 inverse equals the identity. So this is equivalent. We think this is a nicer way to present this, but there's no deep reason why you should use this or that presentation. Okay, and now we're gonna say that a tuple of permutations satisfies these equations if for every pair, for every equation, wi1 equals wi2, when we substitute the permutations for these words, we get the same. We get the same permutation. Okay, so these are going to be the solutions. And as before, we're going to define that we are going to say that a tuple of permutations is epsilon far from being a solution if for every solution tuple, the distance, like the sum of distances of sigma 1 from tau 1 and sigma 2 from tau 2 and so on is at least epsilon, the distances in the Hamming distance. Okay, so this is a general way to write a system of equations and permutations, and now we're going to want to ask the same question. Given, like, is there an algorithm, given some system of equations E, is there an algorithm that takes as input some tuple of permutations and manages to distinguish in a constant number of queries between these permutations being a solution and the permutations being epsilon far from a solution? So this gives us, again, the definition of a tester. I do need to mention, so this is pretty much, this is the exact definition we used for x, y equals yx, just generalized to a general system of equations E. I do want to mention here that when I say that the algorithm is allowed to query the entries of the permutations, it's also allowed, by this we mean that it's also allowed to query entries of her inverses. Okay, so not only are we allowed to query a of like sigma 1 of x, we're also allowed to query the inverse of sigma 1 of x. And we didn't need this. We didn't need this for the case of x, y equals yx, but sometimes in some situations we do need to do so in general. Okay, and again, we're going to say that a system of equations is testable if every epsilon admits an epsilon tester. And again, we have the natural sample and substitute algorithm. So this algorithm with repetition factor k runs for k independent iterations. In each iteration, we sample some x at random. And because the system of equations might consist of many equations, I mean, for x, y equals yx, we only dealt with one equation. But in general, we're also going to sample one of the equations each time in each iteration and test whether that specific equation is violated in that specific x. And we can also define the local defect. So this is going to be the average over all the equations of the number of the normalized number of violations of this specific equation. And the important thing to notice here is that again, the rejection probability of one iteration of sample and substitute is exactly equal to the local defect. Okay, so just as before, understanding which systems does E work for is equivalent to just getting lower bounds on the local defect. It's the same thing. And of course, one of the ways to define the notion of stability in permutations is exactly in terms of lower bounds of the local defects. So we say that the system of equations E is stable in permutations if every epsilon has some delta, which is a lower bound on the local defect of tuples that are epsilon far from being a solution. So just by the same sort of analysis we did before, we just got an equivalent definition for stability. And this definition says that and the system of equations E is stable if, for every epsilon, there exists some repetition factor k, such that sample and substitute with k repetitions is an epsilon tester for E. In other words, the system of equations is stable if and only if it is testable by a family of sample and substitute algorithms. And furthermore, we even have this nice quantitative relation that, like the largest delta you can take in the first definition and the smallest k you can take in the second definition are just asymptotically inverse to each other. And this is exactly due to the same kind of analysis we did before for xy equal yx.
Sorry,
Okay.
is this difficult to prove?
Sorry, the fact that they're inverses to each other?
Yes, with any possible algorithm.
No, so this is not with any possible algorithm. This is okay. So this is crucial, right? Stability. Okay, this is actually exactly anticipating my next slide. So this is what's called an excellent. So this is this is exactly what's called an excellent question, I think. Yeah. So the crucial thing to note here is that stability is equivalent to being testable by the sample and substitute algorithm, but not in general. So exactly the natural question, right? I started with this talk by asking which systems of equations are testable, and until now I only concentrated on one specific, very natural algorithm. But of course, the question is it the only one? So we know that many systems of equations are not stable, and by the equivalence we've just shown, that also means that we're not going to be able to test them by the sample and substitute algorithm. But can we test such systems of equations in general? So the spoiler for the rest of this talk is that for some systems of equations, the answer is going to be yes. And what we're going to discuss from now on is what can one do other than sample and substitute, and which systems of equations in general are testable by some algorithm. Okay, so I'd like to introduce a stronger testing algorithm, which in some ways you can say in a way that it generalizes the sample and substitute algorithm that we've seen before. And in order to do that, we need to introduce a more combinatorial or geometric point of view of these permutations. So I'm just going to define what I guess, well, I guess most of you would just recognize this as a group action graph, but I'm actually going to define it without any reference to group actions. Given a tuple, so the point that I want to do here, just before I introduce the general testing algorithm that we're going to use, I want to somehow get a different point of view of the tuples of permutations that we're going to test. So we're going to encode any tuple of permutation, these are the inputs for our algorithm, as a directed graph with labeled edges. So this is a very simple graph to explain. The vertex set is just going to be 1 to n, so these are exactly the objects that permutations act on. So recall that we fixed some alphabet S that consists of the letters S1 to SD. So if the I permutation takes X to some Y, then we're just going to have directed edge from X to Y, and this edge is going to be labeled SI. That's our graph. Okay, so this is a very natural way to encode these permutations, and just as a sanity check, note that in this graph, every vertex has in degree d and out degree d. And specifically, for each I between 1 and d, each vertex has exactly one ingoing edge and one outgoing edge labeled I. Okay. And the reason we wanted to introduce this graph is that now it's easy to talk about sampling balls in this graph. Okay, right. Okay. So we're going to denote the balls in this graph by BR of x. Okay, this is going to be the ball of radius r around some given vertex x, and just because this is a directed graph, there's some ambiguity here, which I'll explain. So I'm also going, in this ball, I'm also going to be walking backwards and edges. Okay, so think of these balls as being sampled from the graph when we think of it as being undirected. Okay, so we allow ourselves to walk either backwards on forward or forward on edges, and the ball is going to include any vertex that's of distance of at most r steps from x by walking in either direction on edges. Now, when we sample a ball from this graph, we're going to ignore the labels of vertices. So I don't care if I sample, like if the middle vertex is called 1 or it's called 3, and I don't care if like this edge takes me to 5 or to 7. However, I'm still going to care about the edge labels. Okay, so now when I sample a ball from this graph, imagine that I get some sort of isomorphism class. Like I know it, like after sampling the ball, imagine that I now know the isomorphism class in the, among all directed graphs with labeled edges labeled by S, I know the isomorphism class of the specific ball. Okay. And we're mostly going to be concerned with sampling randomly centered balls of some given radius r from this graph. So we're going to denote by ngr the distribution of those isomorphism classes. Okay, so ngr is the distribution over all the like something exponential, like some number exponential in r of all isomorphism classes of edge labeled graphs of radius r. And this distribution is just exactly the distribution of which isomorphism class I get when I sample this isomorphism class centered on some specific x. Okay. So are there any questions so far? This would be a good place if anything is not clear. Okay. Okay. Yeah. So the one thing we should note here is that because this graph has constant degree, right? It's not. It's only bounded by d. That means that for any constant r, there's only a constant number of different isomorphism classes that a ball can take. So this is independent of n. No matter how large the graph is, once you fix r, the number of possible balls is a constant. Okay, so this n is so this ngr is a distribution with constant with bounded size support, bound size finite support. Okay, and this leads us to the algorithm that we're going to use. So this is an algorithm called local statistics matcher. And what this algorithm does is, so just recap, we have a tuple of permutations, sigma 1 to sigma d, and we want to test whether this tuple is a solution for a set of equations E. So what we're going to do is we'll sample independently some balls of some radius r from this graph. And like we have some empirical distribution, which we denote by n empiric. And now the question is, does this distribution look like something we'd expect if our permutations were a solution? Okay. So essentially what this algorithm does is it goes over all the possible solutions to the equations, and it checks in, like you can, and then like for each of these solutions has some distribution of balls, and then we just compare our empirical distribution of balls to the distribution that we would expect to get if our permutations were a solution. And if we're close enough in some metric, which say I fixed it to be the total variation metric, but it doesn't really matter which metric exactly we're using, because we can just, right, we're just thinking of these distributions as, because these distributions have finite support, we're just thinking of them as two vectors. So basically any norm would be equivalent. If our empirical distribution is closer than some delta to that of some solution, then we accept, and otherwise we reject. And the intuition here is that if sigma is a solution, then after, like, if we test enough balls, then the distribution of balls should converge towards a distribution of, towards a solution distribution. So that should work. The question, of course, is about soundness. Are there non-solutions, like are there tuples that are far from being a solution, that are that still have that would still get us an empirical distribution that's close to that of some solution. Before I continue,
Jonathan,
yeah.
There are a few things that a bit confuse me.
Yeah.
So, okay, so maybe you will explain more about this in a moment, but how do you actually approximate this an empirical or
Okay.
go over all solutions and all of that?
No, so actually, okay, so actually, okay, so estimating, yeah, so one of these is, this is related to what I was just going to say. So first, how do we sample an empirical? This is actually not a big problem, because given, I mean, okay, so how do you estimate an empirical? As we said, we just sample k x's, right? We define k empirical as just the actual distribution of over like some k specific x's that we sample at random. And to sample a ball around one of these specific x's, you just need to query, to make some number of queries, which is exponential in R, but is still a constant around this x, right? Like you want to check, say you have two permutations where you're going to check what's a of x, what's b of x, what's a of b of x, what's a of x, what's b of a of x, what's b of b of x, and so on. And you're going to cover all strings of length at most r, and then you're going to get like then you're going to get a picture of what this radius r ball looks like. Okay, because basically just making these queries corresponds to querying an edge of this graph, right? It's like you're in a vertex x, and then you're asking where does the edge labeled s lead to? Okay? So this is how
yeah, Jonathan, this part
now,
is
right.
okay,
Now the other
this part is clear. So you sample k
your other
points.
question is about how do we now measure this distance to, okay, so yeah, so here, this is what I wanted to say. Until now, when we talk about sample and substitute, then
Jonathan, maybe just if somebody stop you, I think it will help to some people who coming from some background to say the words Binyamin Ishram, because if you
Yeah.
I'm
Okay.
sure.
Yeah. I actually that was also planned. It was just planned for the next slide.
Okay.
Yeah. Okay. But maybe okay. But if you stop me, I'll say that. Yeah. Yeah. So first, yeah, the idea here is that let's see. Yeah, no, that's okay. So Binyamin Ishram is going to come in the next slide, but now what I'll just want to answer Michael that okay. So when we talk about sample and substitute, the number of queries that the algorithm had to make and the runtime were essentially the same. Right, because all the algorithm had to do with queries just check whether there is a violation and reject if it found a violation. Here, the number of queries is not that large as long as R is not too large, as long as R and K are not too large. Like as long as R and K are constants when the number of queries is a constant. But I do have this mysterious step here of if there exists some solution tau, which is close in total variation metric to an empiric. The question is, how does one implement this? So in general, I don't have an efficient way to implement this. I mean, the way I have to implement this here would be to go over all taus and compute for each tau its empirical distribution. So this would, yeah, so this would take some time that is exponential in n to go over all solutions.
It will take more time than just checking that x1, xk it's a solution, no?
Right, that's true. However, this is so there's two yeah, but there's two I think there's two answers to why I think this is still interesting. One is that in general in computer science, this is what's called an oracle model. In an oracle model problems, we sometimes assume that that the resource that we're trying to save is access to the object to be queried. Okay, so here we're still trying to be very conservative in the number of queries to the permutations we make and not in the runtime. So suppose say that to query the permutations, you have to send someone, send someone in truck across the desert for each query of the permutations, but to actually make the computation, you have a supercomputer back home. Okay, so in that case, you actually don't care about the length of the computation so much, but you do care about the number of queries. So that would be one answer to why such algorithms are still interesting to us. A second answer would be that I do believe, this is something we haven't really looked into yet enough, but I do believe that for some more structured systems of equations, this generic step of checking the distance of an empiric from the actual distributions of the solutions is actually something that can be done much more efficiently than this exponential time algorithm. Because I guess for some structured systems of equations, we might just have a description of what these balls should look like. And finally, as we're going to show in the rest of this presentation, from a group theoretic point of view, this definition creates some very nice, just turns out to give quite elegant results, which I guess is another reason that we should be looking into it. Okay.
Can you comment on the issue of perfect completeness?
So here we don't have perfect completeness.
So can you fix it?
I don't know right now how to fix this issue. I mean, yeah. So it's a good question. It's something. It's something that. Okay, maybe I'll say there's gonna be a ton of open questions at the end because I think we're really raising a ton of open questions here. But yeah, and one of these is certainly so this algorithm is not fully complete, right? It's only complete, like the probability of, there's still some small probability of rejecting a solution, and there is a small probability of accepting a non-solution. And Yuval is asking whether we can make the probability of maybe if we can get the probability of rejecting a solution down to 0. And the answer is, I don't know, but hopefully yes.
But I don't understand why we can reject a solution.
Sorry.
Sorry, I
you're
understand
asking what?
now.
Oh, you're asking why one can reject a solution here.
I understand it
The
now.
sample,
Sorry.
So maybe,
the sample is
but
very
maybe
bad.
if you ask, I'll answer anyway. Yeah, because because n empiric is going to, for enough queries, n empiric is going to converge to the actual distribution of a solution, but it's only going to approximate it probabilistically because we're only taking some k queries and not querying all the vertices. Okay. So let's continue. Okay, yeah, so I'd like to give some equivalent condition to when does this algorithm actually work. So we're going to say that the equations E are statistically distinguishable if for every epsilon there exists some R and delta, such that the distributions, like for every solution and for every tau that's a solution, every sigma that's epsilon far from a solution, there is a delta difference between there's at least some delta difference between their R-ball distributions, and this would be a good time to say that this basically means that you can't approximate a sequence of solutions with a sequence of tuples that are epsilon far from solutions in the Binyamin-Ishram metric.
Can you say a word about why you're choosing the total variation statistic rather than something simpler? Is it irrelevant, or is there some reason?
So okay, so if you're not doing anything, if you're not trying to do anything quantitative here, that is, if you're only interested in whether there exists a delta and not in what is delta
then it makes
as a
no
function of
difference.
epsilon, then it makes no difference. And of course, right, so understanding the quantitative bounds on delta here is equivalent to understanding the number of queries that the local statistics matcher would need to do. So as long as you don't care about that, then it doesn't matter which metric you're taking. Once you do care about that, then actually the natural metric to take in order to show that local statistics matcher would be a good algorithm is actually the L2 metric.
Yeah, I would have thought so. Yeah. Okay.
Yeah. But on the other hand, in order to show the universality result that I'm just going to state, then actually total variation seems to be the best metric to use. So this is the one we're using.
Can I ask a question? How does this depend on n?
So yeah, no, so it's very importantly, nothing here may depend on n. That's exactly the, right, so the whole definition of testability, maybe I'll, you know what, maybe I'll finish just stating the result I wanted to state about the statistical distinguishability, and then I'll go back to dependence on n. Okay, so this is statistical distinguishability, and the result I wanted to state is that testability is equivalent to statistical distinguishability, and this is equivalent to being testable by local statistics matcher. In other words, we have this nice non-algorithmic notion of being statistically distinguishable, and we show that on one hand, it's not very hard to see that the local statistics matcher, because what it does is basically just checks whether the distribution of balls is is close to that of a solution. It's not very hard to be convinced, even if you don't see the exact proof in your head right now, that being statistically distinguishable is a sufficient condition for the local statistics matcher algorithm to work. A more complicated result, but not an incredibly, like nothing spectacular is going on for it, just a more technically involved result, is that testability implies being statistically distinguishable. That is, suppose that you're testable with some algorithm. Just assume that some algorithm that does, I don't know what kind of magic it does, but some algorithm manages to test a system of equations. Then that would have to mean that these equations are statistically distinguishable, and that implies that the equations are testable by the local statistics matcher. So essentially, local statistics matcher is a universal testing algorithm. So any set of equations that's testable by some algorithm is testable by the local statistics matcher algorithm. Now, to answer the question from before, I was asked about dependence on n. So again, nothing here may depend on n. So in our definition, the definition of testability says that the number of queries that the algorithm makes must be a constant that depends only on epsilon. But it may not depend on in any way on the permutations themselves or on their length. I can also mention with regard to this that it's of course also interesting to ask what one can do if we allow small dependence on n. I know maybe if we allow, of course, like allowing a linear dependence on n just makes everything ridiculous because then you can just sample the whole of the permutations and then you just know whether they satisfy E or not. But you can try to, I know, like some logarithmic dependence on n and see if that yields you anything better than the constant dependence that we have right now. We haven't looked into this at all, but it's another interesting question. Okay, any more questions so far?
I have one more question about this dependence on n.
Yeah.
This local statistics matching, you have these distributions on neighborhoods in the solution sets that you're trying to say sort of how close you are. To what extent is it true that the distributions that you see on solutions, to what extent are those independent of n?
Okay, that's so you're asking whether, say, for n, you're asking whether, say, are there like there's some n and some n plus 1 such that the solution statistics would look completely different for these two. So okay, so first, that's a good question. I'm trying to think. Oren, do you maybe have something wise to say on this? I mean, Oren Becker, maybe?
Does my mic work?
Sorry?
Does my mic work now?
Yeah.
It has some problems. All I have to say is that this is an interesting question and should be studied system of equations by system of equations. I mean, I don't think there is something general to say about it.
Okay. Yeah. So I tend to agree. Okay. No, but I should mention that at least one of the results we're going to see soon actually relies heavily on some sort of difference between solutions of well, does rely heavily on like checking what happens when you remove exactly one vertex from a solution graph. So this is definitely related to stuff that we're doing. Okay, so we know that local statistics matcher is universal. Now, finally, maybe you can also have some groups in this talk. So I'm just going to quickly remind you that given a systems of equations E, group stability, generally the first thing it's concerned with is let's look at the group that's presented by these equations. So we take the free group Fs and we apply the constraints defined by E to these equations. So For anyone who has never seen this, just think of if you take the free group over two generators and you force these two generators to commute, then you get words where you only care about how many of each generator you have in non-invariant order, and this is just isomorphic to z squared. Okay, and the reason it was observed by Glebsky and Rivera, and then also by Argentseva and Paunesco, that stability is a group invariant. So if you take two sets of equations that are that have the same associated group, then either both are stable or both are not stable. Okay, and we've proven the same for testability. So this encourages us, as is done in stability, to look at the properties of the group defined by E in order to understand whether it's testable or not. And now I can finally show you some results about systems of equations that are testable. So of course, any systems of equations that's stable is also testable, right? Because it's testable by the sample and substitute algorithm. But what about systems of equations that are not stable but are still testable? So now I'm going to show you some of those. So here are some positive results. So first, again, for the non-group people here, we say that a group is amenable. We're only wrote finally generated group. Maybe what I'm saying is only true for a finally presented group. I apologize if this is not accurate. But for the non-group theory people here, we're gonna just think of an amenable group as a group with a Cayley graph that's very non-expanding. Okay, it's the opposite of an expander. And there's a result by Becker, Lubotsky, and Fon that just characterizes, among the amenable groups, it characterizes all the stable ones. Okay, so this says that if the group associated with gamma, if the group associated with E, if that group is amenable, then stability of a set of equations E is equivalent to the condition that every invariant random subgroup is cosophic. And you don't need to know what's invariant random group and cosophicity is right now. You just need to know that they give some non-trivial condition on which amenable groups are associated with stable systems of equations and which are not.
We will make sure that at some point in this seminar,
of course, yeah, I assume
what is IRS, the invariant random subgroup. It's a very important notion in group theory, and it's interesting that it came up in the connection with stability in a somewhat surprising way. Yeah.
And we prove this is actually really not hard to conclude just by looking at the proof of the Becker-Lubotsky-Fon theorem. It's not hard. Like once you have the notion of the local statistics matcher algorithm and statistical distinguishability, we can just look at that proof, and you see that actually it also shows that if E is associated with an amenable group, then it's always testable. Okay, so for amenable groups, we have some condition, some IRS condition for stability, but testability is always true. Okay? So that means that if I have a set of equations whose associated group is amenable, but doesn't satisfy this Becker-Lubotsky-Fon condition, then I got a system of equations that is testable by the local statistics matcher algorithm, but is not stable. So it's, say, not testable by sample and substitute, okay? Because that would mean that it's stable. So here's a set of equations. It's not incredibly intuitive, but this is a classic work by Abels that gave a finite presentation of the group known as Abels's group. And this group is exactly that. It's amenable and doesn't satisfy the Becker-Lubotski form condition. So this is a concrete set of equations that we now have a tester for, and we didn't before. Okay? So this is our main positive result, that amenable groups are correspond to testable systems of equations. On the other hand, we also have some negative results.
I just want to barge in for a moment.
Yeah.
Can you go back to the previous slide?
Yeah.
With Abel's group. So it's just worth noting that if all you want is a group which is testable but not stable, you can take every amenable group which is not residually finite. Yeah. So Abel's group is actually residually finite, but still it is an example for testable and not stable. But any amenable group which is not residually finite is testable but not stable. So you have a family of examples.
Okay. Now, on the other hand, we also have some negative results for testability. So, right, the other natural question, other than does testability give you something that stability doesn't, which we just shown is true, is there something that you can't test? So that brings us to the other side of the spectrum from immutability. So we're going to look at groups with property T. So again, for the non-group people here, just think of a property T as saying that's not exactly what property T says, but for our goals that suffices. Think of property T as saying that that the family of connected solution graphs for E is an expander family. Okay. And maybe, yeah, okay, no, I'll keep it at that.
For the professional, this is exactly what is called property tau.
Yeah. Yeah, in the actual the actual paper actually.
A name due to the man selling it.
Yeah. Yeah. So in the actual paper, we actually work with property tau rather than property T. So we get a slightly stronger result than the one that I'm showing here. Okay, so again, we have a negative result about stability due to Becker and Lubotski that says that if the group associated with E is infinite and Sophic and has property T, then it is so you can think of this as having property T and some pretty easy to satisfy conditions, then in that case, E cannot be stable. And we just almost say that this is also true for testability. We need a slightly stronger condition on the group gamma. We wanted to have finite quotients of unbounded cardinality and to satisfy property T. And then we have that the equation are also not stable. So this is mostly a strengthening of this theorem about stability. So property T doesn't allow you to be testable. And again, I have here some equations which one cannot test. So the special linear group over the integers for any n larger than 3 has property T, and the equations associated with this group are not testable. Okay, these are our results about the stability so far, and I think
Jonathan,
a lot of
if you will have time, in the Alex's and the Oren's paper, they define new notions of stability that they call flexible and very flexible and so on.
Yeah.
Do you have your analog of
yeah, we have, so this is again anticipating a bullet in my next slide. So yeah, I might just get to talk about this in a minute. That's a good question. Yeah. Okay. So before going to final slide, I just want to say
Can I
that.
ask a question? Yeah. Now, but I missed the first lectures. I'm sorry about that. So these are you in terms of the group. You've given a solution for the amenable and I guess a negative result. I'm not sure. How does that fit into the testability paradigm? I mean, what's the bigger picture here? I mean, does this?
Well,
I'm not sure I follow.
Is that we don't have yet a bigger picture.
Yeah.
And part of the seminar is really to develop, or the whole area in this time is to develop techniques to prove results on stability and testability on one end, or on instability or intestability on the other end. So more or less so far, you can say amenable are always testable, in many cases that we, in some sense, understand, also stable, though I have to say that the condition about the IRS is not so easy to implement, but at least it's a calculation. And there are a lot of groups which are not, but there are many groups which we don't know, take a surface group, many simple kind of groups.
Okay, so that's the group theoretic question, and I understand that that's an interesting group theory. I'm more in terms of locally testable codes or something like that.
Mm-hmm.
Okay.
So I'm trying to understand the picture of there you're trying to make specific codes which would be locally testable. This doesn't show that that's impossible.
Yeah. So I think the answer to your question is that we're still trying to draw the picture. So this is really the first work about the stability of equations and permutations. And we do feel that there is a lot of potential here. And one of the goals is to try and bring together group theorists and computer scientists and combinatorics people on this. So far, most of the work on stability has been from the point of view of group theory, obviously, because it's a group theoretic concept. But there's also been some work, say, the work by Oren and myself on quantitative stability that took more combinatoric approaches. And we are hoping that this is something that can happen more, and maybe we can really have this subject touched by people on both ends of this. And it would be really interesting if these equations and permutations turn out to have some use in classic questions like locally testable codes, or can we relate them to other notions in property testing, or PCPs, maybe, anything like that.
In a way, you see, the set of solutions here is like a code, and if you prove stability results, then you prove that this is a locally testable code. The problem is that even if you are willing to accept non-commutativity, which is not the problem, is that it's a code with a very small rate. For example, the number of pairs of matrices of permutation which commute is very small with respect to the total number of permutation. And the big problem in locally testable code is not to find locally testable code. There are locally testable code, but the problem is to get good code that the rate will be at the same time also good. And that's, at least so far, we cannot claim that it can come from this direction.
My opinion here is that locally testable codes are a very good analogy to what we're doing, but I don't think this is actually going to be directly useful for them. I think this would have to find its own. I think this is going to be useful for things, just we still need to find what exactly this is. And this is part of the reason we'd like to get a lot of people exposed to this.
That's a good answer. I was just trying to get the big picture, and I think you.
So with these motivating statements in mind, let's spend the last few minutes just quickly going over some of the many questions we have for further research here, and these are motivated both from a computer science perspective and from a group theory perspective. So one would be, I guess, So right now, the only testable systems of equations that we know are amenable, and it would be interesting to find others. So, for example, the equations xy to the m equals yn to the x for m and n larger than 1. These are the Bauslag-Solitar equations. These are not stable. And we really have no idea right now how to approach for the question of vertistability or lack of thereof. So this is just an example of pretty simple equations that one can look into. There's also from a nice thing is that from a computer science point of view, so, okay, so the notion of testability that we're using in this work translates nicely to this statistical distinguishability property, but it's a weak notion of testability due to several reasons. So first, our testability is not uniform in epsilon. That means that recall that we wanted to have for every epsilon, we are asking for an epsilon tester. While you can also talk about, and this, I think that the more, I mean, this, okay, so our definition of testability has definitely been used in some very important works, but the more common definition of testability asks for a single algorithm that takes epsilon as a parameter. Okay, so that would mean, so just to understand what's the difference here, right now we have some algorithm that makes, takes k samples of balls of radius r, and these k and r are just some constants which depend on epsilon, but we don't actually require the algorithm to compute them from epsilon because the algorithm is just some fixed algorithm for every epsilon. If one can actually compute r and k from epsilon, then you can generate this uniform algorithm. And one can conjecture, just due to the way these things work with amenable groups, that maybe if the Fellner function of the amenable group is computable, maybe one can get uniform testability. Anyway, it would be interesting to understand from a group theoretic point of view, does uniform testability correspond to any natural thing in terms of group? There's also the stronger notion of there's also a stronger notion. I see Yuval just sent me a link here. I'll look at it soon. There's also a stronger notion of POT testability, which one can think of again. So in the local statistics matching algorithm that we gave, the radius that we're, I mean, the radius that we're sampling the balls with is growing in epsilon, right? For every epsilon, you need a larger size of ball. And POT testability generally captures the notion of what if epsilon does not have, what if epsilon may not depend, what if the radius may not depend on epsilon? What if you just want some constant type of sample that you do no matter how small epsilon is? And note that this is, for example, what the local statistics matcher does, right? The sample is always of the same, like it always samples the same equations. It doesn't need like bigger and bigger balls the smaller epsilon is. So POT testability is another very natural type of tester that would be interesting to also understand from the group theoretic point of view, and maybe understand when do we have these for certain for given equations. I guess maybe I'll skip the efficiency things for now and just mention flexibility in a few words. The flexible model is a slightly weaker notion of stability and of testability, where when we consider the distance from being a solution, we don't only consider the distance of a tuple of permutations over n to another tuple of permutations over n, which is a solution. We also allow n to change slightly. So we can also like think of this as, if you want to take your graph and fix it into being a solution, you're not only allowed to change the edges, you're also allowed to remove or add a small number of vertices. Okay. So this makes it easier to be stable because your set of tuples that are epsilon far from being a solution is a smaller set. And there's some very interesting work on this done about this for surface groups recently. But in general, it would be, we don't have any negative testability results in the flexible model, for example. So that's another thing that would be very natural and interesting to research here. Okay, I think this is a good place to finish. So thank you very much. I really enjoyed your questions.
Thank you. As our time is over, and I know at least here locally, some people want to go to lunch. Let's be just short. If there are some questions, then please very quickly speak out.
I have one quick question. So the Binyamini-Schramm convergence usually only involves most of the eigenvalues converging rather than your property tau, which I like very much, demands the gap, while it seems to me that if there were bad eigenvalues near the top, everything would be the same. So especially if you're using Binyamini-Schramm, which is a statistical statement, which is am I wrong?
Maybe we are not yet there, you know. This is so now this is the Sarnak density conjecture.
Yeah, right. I was wondering whether that's the more.
Eventually, we may come. We may.
It just seems in your examples you showed that you're not testable by using the stronger property, but it seemed like you were going through this IRS.
Yeah.
IRS, is that what it's called?
So, but for the negative example, for the negative examples, the negative examples are not related to IRS though.
Okay, all I'm saying is that Binyamini-Schramm convergence means that the eigenvalues converge to a limit distribution, which is kind of the cover that the things are converging to, and it usually allows many outliers. Okay, it's just a comment.
Yeah, so
it's a good question. I mean, the proof, it's actually the proof for the negative results is very combinatorial and hands-on, so it shouldn't be very hard to understand whether we can use some weaker assumptions there.
Your paper's on the archive?
It's gonna be in 2 weeks, I guess.
Okay. I'm pretty busy. I'll wait. I don't want to keep you. Okay.
Yeah, some more questions quickly. And if not, let's thank Jonathan. And next week, Oren will talk about some more, I guess it's going to be a mainly negative results, if I remember correctly. But eventually we'll have some positive approach to the subject with some positive results also. Okay, see you all next week. Thank you very much. And thank you very much, Jonathan.